Okay, all yours, Dennis.
Somebody see if I'm clicking the refresh there.
You are.
Okay, good. Should be good then. All right. Well, yeah, it's really fun to be back here at CJUG. It's been a long time since I last did a presentation or attended one of the meetings. I do make a trip back here every year and visit Seattle at least once a year. But usually the timing doesn't work out to actually come by. So this year I made a special effort to make sure that I'd be here for this event and a couple of other events too while I was at it. But it's great to be back at CJUG in particular. Now, about me, I'm a Java and Scala developer, writer, consultant, training instructor, all those things, all in one package. Open source developer, that's always been one of my interests for, oh, I don't know, at least 15 years now. I think I've been participating in the open source development field. The main things I'm involved in currently are Apache DXF, and the JIVX XML data binding is a project that's pretty much been put on hold now. I'm not really doing any active maintenance of it or anything, and some other older projects as well. I'm also an author, mostly for IBM Developer Works these days. My current series is JVM Concurrency, and I'm going to be showing you some things from the series today, including some coverage of stuff that I haven't gotten to in the series yet, but hope to soon. Most of my recent experience has been in enterprise systems, data integration, web services, that sort of thing. That is kind of my mainline work still. For most of that, I'm not using Scala currently. I'm just starting to get Scala into some of the projects where I can sneak it in without too much trouble. Consulting and training service clients worldwide. Yes, and somehow I didn't get the refresh that I was looking for there. What's the key code to do a refresh? Is that 5? Do I know? Should be.
Control Alt.
What is going on here? Why didn't I get it?
Control R.
Oh, I added to the wrong slides. Oh well. Okay. What I didn't put on there is that performance is a special area of concern for me and something that I feel I have a lot of expertise in. Nimrod, who has stepped out for the moment, the first thing I did with him was actually a project for a company here in Seattle. Nimrod had been working on it, and they brought me in as a consultant because their performance was a couple orders of magnitude below where it needed to be to get the next round of financing. So in a couple of weeks of work, we got it back up to the level that was required, which I thought was pretty impressive. Financing didn't come through anyway. This was back around the 2000 crash time. But at least they did make their goals in terms of performance. It's something that I've been following for a long time though. I started out on computers that had performance probably about 5 orders of magnitude below what we've got now in typical systems. So there's been a lot of increase in performance and capacity in systems in the time that I've been doing development work. But despite any increases, and no matter how much faster the systems get, you're always going to have applications that where performance is an issue. And that's not necessarily the typical like desktop application or such, but there's going to be server-side applications and that type of thing where performance is an issue. And that's something where I feel I am. I have got special expertise and do like working. So concurrency basics. Well, this is kind of the outline of what I want to talk about tonight. We'll talk about concurrency in both Java and Scala to start with, before I get into the actor model and Akka in particular. And I'll finish talking a bit about retrofitting Java applications to use Akka, and a couple other issues around the Akka stuff.
Are your slides available on the web?
I'll get them out there before long anyway. I'll try and send you guys an update when I do. I've been kind of busy on this trip, but I'll be home soon, and we'll have time to get stuff organized a bit better then. But yes, I'll make sure that they get out there within a week or so. And so starting off, what's concurrency? Well, concurrency has been something that's been a theoretical topic for many, many years in computers, but it's become more and more of an active topic as we get into the current situation, multicore processors and everything. It can be a lot of different things, a lot of different ways of performing multiple computations more or less simultaneously and potentially interacting. So time-shared computations on a single processor, computations running simultaneously on multiple cores within a processor or node, and computations running simultaneously on physically separated nodes. So these are all different stories or different forms of concurrency. Now, it's been around for a very long time, but it is becoming more and more of an issue for us because processors are no longer growing so much in clock speed. Around 15 years ago, 14 years ago, thereabouts, around the turn of the century, we found that processors had pretty much peaked out in performance. They have been continuing to increase since then, but not by leaps and bounds. I think, let's see, the first gigahertz processor came out probably about 2001, 2002, anybody remember? Let's say 2001, 2000. And the current top-of-the-line processors are probably about 4 gigahertz, roughly. So say it's gone up by a factor of 4 in roughly 13 years' time. That's not much of an increase by historical standards. It used to be that it was doubling in speed every year and a half. So what people are doing now, what the manufacturers are doing now, in order to add processing capability to their cores, is they're adding more and more processor cores to the systems. So rather than adding more processing capability to their chips, I suppose is the best way of putting it. So now performance grows mainly by adding cores. 4 more cores now come on everything, including cell phones. Likely be 16 in another 10 years, or even more than that. So we need to worry more and more about using concurrency in order to make use of those multiple cores. I said before that concurrency didn't necessarily matter that much for, well, I said performance was not necessarily an issue that much for end-user applications and everything. But that's a conditional thing. It depends on what you're doing. For many types of applications, even on a cell phone, you want to have good performance, you want to show everything working properly, you want to have a smooth UI, and that requires concurrency even when you are just working on a cell phone. By using concurrency, you can make use of the multiple cores, and you can do separate things that aren't all tying up your main thread. So concurrency is something that we all need to worry about increasingly. Concurrency across systems is also becoming more and more of an issue all the time. Enterprise applications need to be scalable. That's why so many things are moving to the cloud and into cloud deployment where you can add more processors as needed. And that's fine for doing certain types of operations. Coarse grain scaling distributes users across multiple systems. And that's mostly what people are doing in the cloud world. They're taking a particular application and just deploying that application across a variable number of cloud processors, cloud systems. And then as demand grows or shrinks, you can take some of those systems offline or bring new ones on. And everything scales up automatically because you can just shuffle users across a wider or smaller number of systems. But it doesn't help with response time for more complex requests. So it helps you keep the average response time down as your number of users grows, but it doesn't help you process any single user any faster than you would otherwise do. Finer grain scaling has the possibility of allowing you to get faster response times for an individual request. So you can still add systems as needed to handle increased load. You can distribute tasks based on interactions. And if you set things up right, at least in theory, you can do faster processing of complex requests than you can just with scaling the application across multiple systems as a whole. Concurrency does have some limitations. The performance gain from concurrency is always going to be limited by what you're doing. In terms of doing more of a task, something like the example I used of cloud deployment of an application, where the same application is just being deployed in more and more systems, well, you're going to be limited by the number of communications and coordination required between the different instances. So if your application uses a database as a core part of its functionality, you can distribute that front-end code across an ever-increasing number of systems, where you're going to hit a bottleneck when you reach the capacity of the database if everybody has to share that. If completely independent, then you have unlimited scalability for spreading something out. So really the only example of that they could come up with is something like a static website or something that just does some computation or something. Most interesting websites or server applications of any form are going to have limited scalability because they're using some kind of shared resource, and you're going to have communications overhead and coordination as part of that. For doing a task faster, you're going to be limited by the amount of the code, the percentage of the code that can actually be made concurrent versus sequential. There's something called Amdahl's law. Who here remembers CDC systems? We got one, we got two, three, okay. You're the only ones who would date themselves on this, huh? I remember CDC. Ah, yes, it was a fine old company back in the day. Gene Amdahl was the guy who got that started. He did the design for CDC, and then he had his own system after that. I've forgotten, was it Sequoia? Something like that.
He built IBM 360 compatibles.
Oh, okay. But Amdahl was one of the big people pushing the limits of supercomputers back in the latter part of the last century, last half of the last century or so. So he came up with a law that said if you're going to make use of concurrency and parallel processing, that sort of thing, the maximum gain that you could get is going to be proportional to how much of the code can actually be executed concurrently. If 95% of your code can be executed concurrently and 5% of it has to be sequential, the maximum amount of performance benefit you're ever going to get is a 20 times performance increase because that 5% is going to limit you. More likely, if it's like 75% of your code can be executed concurrently and 25% has to be done sequentially, then the maximum you're ever going to get is 4 times performance gain, no matter how many processes you throw at. So you're going to be limited by the proportion of code that has to be sequential. You're also going to be limited by external delays if you're doing anything that involves communications or any kind of external stuff. I/O, talking to a disk drive, talking to anything external, basically. Now, let me make sure I didn't go through multiple slides there. Yeah. Okay. Now, when you start working with concurrency and handling interactions between different processes or different things that are going on in the system, you have to have some way of communicating completions and communicating information about the status of things between the different tasks involved, whether those are threads or whatever units of granularity you have there. So concurrency requires handling asynchronous events. There are two basic approaches to handling asynchronous events. You can basically have a thread wait for something and just go to sleep until it's ready to go. Or you can have the event provider somehow signal when something is ready. That can be as simple as setting a flag that can be pulled by the main thread. It can be executing application code supplied by the user, which I consider a form of callback one way or another. Or you can add event to a queue or something of that type to say that it's complete. Blocking is generally considered a bad thing, at least when you get into heavily scalable applications. The reason is that blocking is going to limit both performance and scalability of your applications. Blocking ties up threads, and these are a limited resource. For modern systems, the number of threads that you can have on a system is going to be in the tens of thousands. So it's not as limited as cores in the processors, for instance, but it is still limited. And if you're processing hundreds of thousands of requests a second, then it's a very real concern. Even if you're processing 1,000 requests a second, it's probably going to be a real concern. So blocking ties up threads, number one. A thread has to wait for something to complete. It also adds overhead from context switches. Now here again, we're not talking about an immense limitation from this or a huge impact. Context switches, I did some timing exercises for a recent article, and it came out to be on the order of, I don't know, tens of microseconds to do a context switch, running on my laptop system, which is a little bit dated. So typical server systems are going to be down probably in the single-digit microsecond range. So it's not very much time. On the other hand, if you think of it in terms of processor execution time, it's tens of thousands of clock cycles, tens of thousands of execution times, instruction execution times. So it is a significant overhead certainly. Even worse from some standpoints is that you can have unpredictable latency when you're doing thread switches, context switches. The reason for that is that modern systems don't keep all the cores running at full speed all the time. They power them down and put them to sleep when you have the chance to do that. It's a requirement of most of the CPUs, most of the chips that are coming out these days, that actually be done. Because if the cores were all running at full speed all the time, the chips would melt. They're not designed to support that. So the systems have to power down the cores that are not in use. And if they get too busy, they actually have to throttle them back so that they're not getting too hot, or maybe switch between cores periodically, or that sort of thing. But context switches that require a core to come back from a sleep state can take potentially milliseconds of time. And that's kind of a nasty hit if you're doing an application on server-side stuff that's doing something like stock trading, or these fund trading where they want basically response times in the hundreds of microseconds, not in the milliseconds. So non-blocking is best for scalable applications. And that's going to be something I talked about a lot here today. Java 8. How many of you have started working with Java 8? Not too many. I know a number of you at least followed the exchanges we had on the CJUG list. We had some discussion about that back in March when it was coming out and everything, some of the factors around it. Java 8 is really interesting, and it has two big features that are really kind of fun and significant improvements to the language, I think. One being lambdas, which aren't really functional programming, but at least make it look like you're doing functional programming. You're doing interface programming, but yeah. And the other is improvements for concurrency. Java 8 added something called Completable Future. That's kind of similar to what most other languages have, including Scala already. It's a much more flexible form of future than what was previously supported by Java, and allows you to do a lot more things using futures. So in particular, it has a one-time only completion, meaning that once you set the result of the future, it's set permanently. There's no change yet, you can't go back. And it allows a thread to hold or block or use a callback, and it even provides ways of composing and combining features so that you can mix and match them together and have them do kind of a scripted interaction over time. We'll see an example of that in a moment. Java 8 also added streams. Now streams allow you to do computations in parallel when you have a bunch of data to be handled. They're not a general purpose concurrency tool, because in general concurrency involves splitting up different tasks and not just doing the same task on a bunch of different cores. But they're very useful within the limited environment of doing the same calculations or whatever on multiple sets of data. And finally, there's an improved fork join tool from Dudley. But that's something that has been in the works for a while. I'm going to give you a couple examples of Completable Future and using that. Here I've got some code. I'm not showing you everything, but basically I've got some tasks here that are going to complete in a variable amount of time. So I've got the task 1, for instance, is going to complete in 1 second, task 2 in 2 seconds, task 3 in 3, task 4 down in 1 again. And then I have this code down here that's going to run a computation with those guys and return the result as a future. Now in this case, the code is doing blocking. So there's really no reason to return a future except for compatibility with the non-blocking versions. So that's why I'm showing you this blocking version returning a future instead. What it does is it gets the result of task 1 by doing a join. Then it creates task 2 and 3 and does a join on each of those to get the results, and sends that result to task 4, and then returns the result of that one. Anybody know why I'm doing these two futures, creating them like this rather than just doing them in line?
You would block right there.
Absolutely. So I'm doing it this way so that these two tasks can execute in parallel rather than executing sequentially. So I start future 2 and start future 3. And behind the scenes, there's actually going to be an executor pool of some form that Java uses to run these tasks and to actually get a result back from it. So we get the two started, and then I do these joins here to get the results from them. And I join on the result of the final task and give that as a result. Any questions about that? Is that fairly clear, everyone? Yes?
How does this compare to the Scala Future as already promised, or whatever it's called?
Yeah, I'll show you in a minute, actually.
Okay.
I got that coming up. So I just wanted to give you the Java 8 examples first. Too far. So here then is a cleaner way of doing it, using non-blocking code. Now, the top one is the simplest form. The bottom two here are just breaking that down into a step-by-step process. This is actually from one of the articles on IBM Developer Works, so you can see it in nauseating detail there and get all the discussion of it and everything. But basically what's going on there is I'm using these operations that are defined by the Completable Future class to combine Completable Futures and to do things with the results of the two of them together. So in this case, I have a Completable Future Task 2, a Completable Future Task 3, and I define a function, well, an instance of an interface that's going to add two integers together, or add two values together, yes, and return an integer result. And then I say, return task 2 combined with task 3 using the sum function. So what that's going to do is it's going to tie the completion of task 2 to this effectively a callback type thing, where it says, well, once task 2 is done, we're going to want to wait for task 3 to complete, and then when it does, we're going to do a sum operation. But actually, it doesn't wait. What happens is it creates a new completable future for this result. So you have the task 2 completable future, the task 3 completable future, and then we return yet another completable future that knows it needs to take these two results and add them together. Done, here's the mainline code, and all that does is it does the task 1 completable future, and it says then compose with a lambda of this run task 2 and 3. Boy, anybody here who's not familiar with Java 8 and feels like this is all gibberish at this point? I'm using some notations here. This is a lambda type thing. It's a method reference in Java 8 terms, which just says we want to call this method, or we're going to pass this method as a function interface, or as an interface function, whatever. So this says I'm taking task 1, and I want, when it's completed, to compose it with this other method here. This other method takes an integer, which is the result of task 1, runs task 2 and 3, and returns the future from that. And then finally, I take that result of tasks 2 and 3 and compose again, this time with task 4, which was on the last slide. So this is giving you an example of how you can work with futures and kind of combine them, completable futures in Java. Now, if you look at that code up there on top, it is pretty elegant. And once you understand how it works, it's very cool to see something written out that concisely that tells you how you're going to orchestrate these tasks and have them work in combination with each other. Unfortunately, the way that Java works is that it requires, well, let me back up a step. I'm going to show you the Scala code in a moment. And one thing you're not going to really see in the slides is that Scala has a much better handling of functions than Java 8 does. Functions in Java or in Scala are kind of first-class objects that you can pass around. In Java 8, interface instances are what you pass around. Partially because of that, you have a lot of different methods defined on the Completable Future class in order to allow you different ways of combining putting these things together. I think there's like 47 different methods defined. So it's great that we have methods that we can use for composing event flows and all that sort of thing. But it did require a lot of work. It makes the interface really complex in Java 8. One downside.
So Dennis, have you looked at whether or not you could do this with stream generation? Parallel stream generation followed by classic, the collection, the stream processing?
Well, just by coincidence,
Oh, good.
it's not doing the same thing. The reason being, in that last slide, I was dealing with 4 particular events. So they're all kind of different events. The fact that they're all based on the same code is kind of behind the scenes, but effectively they were like 4 different things I'm doing. I'm going off to a database, I'm going off to web service or whatever, and I'm just simulating those with those tasks. Streams, on the other hand, are designed for parallel processing. I don't see any way that you could easily do the sort of thing that I was doing on the last slide with streams. Streams are great when you have a lot of computations to be done over a collection of data, and you want to run those in parallel. But as I said, I don't know any way of using streams to do what I was showing you on the last slide. We can talk about that maybe later on if somebody has an idea. Yes?
So I guess the difference would also be that the completable future lets you basically build an arbitrary DAG out of your different tasks.
Yeah,
Whereas
exactly.
this is more linear, right?
Exactly. We're building a branch tree basically here and saying we want to combine two events, and we're composing events, meaning we take the result of one, give it as input to another, and then we're combining 2 results together and doing something with the result. So completable futures allow you to do, as Eric said, a DAG of what you want to have done. It's basically building a execution flow for your events, or for your tasks. That's probably the best way of putting it. Streams, on the other hand, are taking a bunch of data and saying, well, I need to do this computation on all these values. Can you split it up for me and make use of multiple CPUs if available? That's what the parallel stream stuff does. So in this case, as the comment says, I've got a bunch of chunk checkers. This is actually finding the best match for a word out of a bunch of words in a dictionary. So it's like minimum edit distance calculations. And so I have all these individual chunk checkers that are set up. Each one knows about a bunch of words that it has available. And I want to run them in parallel. So I set up a parallel stream. Chunk checkers is actually a list, as you can see up there. So I do this parallel stream method that gives me back a parallel stream result. And then I say I want to map. So for each checker in that list of chunk checkers, I'm going to run checker best distance on the target word. And I'm going to do a reduce step. The reduce takes multiple results and combines them to end up with a final result. So in this case, I'm saying I want to find the, basically I'm doing the best match of the possibilities there. So it's saying that I'm going to compare with the worst match possible and then take the best of the 2 as the result. So just finding what is going to be the best result of all the ones I got back. What happens behind the scenes is when you do this parallel stream and then do something like a map operation or one of the other parallel stream operations, it goes to an executor that will have multiple threads. Typically, it'll have a number of threads that's based on the number of cores in your system, generally +1 or +2 or something like that. And it will distribute the work to be done across those different cores. And then once you have run the individual cores, it'll combine the results using your reduce function to actually come up with the final result.
Is that controllable, the number of threads versus number of cores?
I'm sure it is. That's a good question, but I don't know how offhand. I think you'd have to set it. I think there's a effectively mutator you can do on there to set a specific executor or something. I'd have to check though to see. Any other questions about that part? All right, let's move on to some Scala stuff then. Scala concurrency, it's had similar features to Java 8 for some time in a lot of ways. And in fact, I think that some of the Java 8 changes were, if not actually modeled on the Scala stuff, at least they were heavily influenced by it. So Scala has a promise in future. Rather than just a completable future, it has its pair. A promise is saying that at some point in the future, well, I'll fulfill a future for you. And a future comes from a promise that somebody is making. You can pull, block, use callback, or use standard collections methods on these futures, as we're going to see in a moment. It also has streams. I'm not going to show you an example of Scala parallel streams. It's fairly similar to what we have with Java, a little bit different in that Java actually takes a collection and transforms it into a parallel stream, whereas with Scala, it's just a slightly different variation of collection that supports the parallel operations. So some subtle differences there, but in effect, it does the same sort of thing behind the scenes. And it even uses the improved fork join tool. In fact, the improved fork join tool code actually came about largely through some problems that they ran into in Akka with the threading issues. And then it got back ported to Java 8 as well. There's also a very nice feature in Scala called the Async Mapper that makes it much easier to coordinate these kinds of things and make them work together. We'll see an example of that in a moment too. Right now, let's take a look at promise future with blocking code. So here I've got the equivalent of the Java code that I showed you for Completable Future. I've got the 4 task definitions, the same as I had in Java, and then I have a blocking code variation here that's doing the same thing I had in the Java code, just using Scala instead. So it does this await rather than just doing a join was the Java equivalent on the future. So pretty much the same as before. It also has this promise structure, which Java didn't have. And you notice I create a promise, I set a result on it, and I return the future from that promise. Well, that seems kind of backward. But again, this is using blocking code, but for compatibility with the other versions I was doing everything, I wanted to return a future. So just like with the Java blocking code, this is returning a future that's already complete. So it's a future past, I suppose. All right, non-blocking. Well, this is one of the ways of doing non-blocking code with Scala futures. It is just one. There are a lot of different variations that you can take. The nice thing about it is that it's using general purpose methods or whatever operators that are defined in all types of collections. So in Scala terms, a future is effectively a collection of 0 or 1 objects, if you want to think of it that way. It's either going to be a successful result or it's going to be a failure result, but it's not going to be either of those until some point, when it's actually fulfilled. So flat map, in Scala terms, is taking the future, it's taking the result of that task 1, and then using it for another function, it's input for another function. So in this case, I've got task 1, flat map, and I have v1. Well, that's saying take the value, the result of task 1 as v1, and then we're going to do this with it. We'll create task 2 and task 3, and then I'll flat map each of those as well, and finally end up with the task 4 result. So that's one way of doing it in Scala. I think it's probably about the cleanest way, though I'm not sure about that. Anybody here have experience with Scala and having other suggestions on that? No, nobody's going to volunteer. Okay. There's also something called a for composition for more complex cases. In this case, flat map was actually doing what I wanted, so I just used it directly then. But for those of you who are Scala aficionados, I didn't want to miss out on mentioning for compositions. Now, there's another approach in Scala that is really very cool, and it's based on a C# and F# feature, but I think that the Scala implementation is much nicer than what they have in C# and F#. I'll explain why in a moment. The Scala macros perform compile time transformations of code. Now, macros are a general feature in Scala. It's not just for this async macro, but this async macro happens to be probably the most exciting and significant use of the feature so far. But in general, macros can perform any kind of transformation you want. It's not completely set in stone yet how they're going to work, though. They are still being tweaked in terms of the implementation of macros. So we don't know exactly how it's going to be in there. If you write a macro these days, you may have to make some changes to it for the future. But the async macro, I believe, has been committed as something that is going to be part of the Scala language before long. Right now, it's actually an add-on that you have to do separately. But it works fine and very useful. What I'm doing with this async macro is I'm converting what looks like sequential code to asynchronous. So this looks like the blocking code that we saw before. It says, value v1 is awaiting the result of task 1. Then value a is waiting, as the result of task 2. Value b is the task 3 result. I'm going to wait for b and a and b and pass them to task 4, and I'm going to wait for the result of task 4. So that looks like standard sequential code, like blocking code would be. But it actually converts that with the async macro into something completely asynchronous. And I'll show you on the next slide how that works. So a very powerful abstraction that really gives you ways of flexibly composing events and making them do different things. Whoops. So async has several effects. That not a keyword, but the macro. Declares the block to be asynchronous that you're working with. It executes the block asynchronously by default, meaning that when you have this async block embedded in your code, it's going to execute that asynchronously no matter what. Now in this case, I've got a method that actually returns the result of the async block, which is going to be a future. But I could just as easily have this embedded in my code directly. It doesn't have to be in a separate method. That's one thing that is superior to the C# and F# implementation. From what I know, those require it to be a method that is actually tagged as async. But in Scala, you can embed it anywhere in your code. It's not a limitation that way. So it executes the block asynchronously, returns the result as a future. It allows non-blocking await to be used inside the block. And it effectively suspends your code at that point when an await is seen until the result is available. What actually happens behind the scenes is that that async macro generates a state machine class for your code. And it's going to attach to the incomplete handling for each await return, and completion passes failure and moves to the next result. So if we go back to that sample here, what this is actually going to set up is the initialization code for the start code for async for this block is just going to create an instance of task 1 with this one parameter, and then we immediately hit the await. So it's going, because that's a future. So it's going to attach itself as a listener basically on that future, and when the future completes, it'll get back a callback essentially and say, oh, okay, I'm waiting for the result of task 1. Now it's available. So let's change state and go on from there. And you'll see the next thing is I'm going to take the value that was returned and use it in task 2 and also in task 3 before I hit the next await. Yes, sir?
So since we're returning a future, why do we need the last await?
Because the async block itself is returning a future.
Okay.
So the async block itself returns a future. If I didn't have that await in there,
Would be future
it
with
would be a
future.
future of a future. Yep. Okay. So it's very cool, a bit complicated, but cool, and it works very well. Now there are some limitations because of the implementation. You can't use await inside a nested closure like a function definition or a class definition or anything like that, because it's actually a state machine. It's not it's not, it doesn't know about nested closures and all that sort of deal. You can't use a wait inside a nested try-catch block either, for much the same reason. Try-catch gives you nonlinear execution, and you can't really model that in the state machine. And finally, debugging can be confusing, as with other callback approaches. Well, that's one thing that everybody who works in concurrent code has run into, I think, that you get into situations where you're processing an event, and the source of that event is some asynchronous computation that's not part of your mainline code. So you're kind of jumping through your code to have these completion functions and to do things in different places when something completes. So you run into the same issue with this. If you're executing that code from the last slide, and let's say you set a breakpoint here, you get that breakpoint, but when you looked at your call stack, you would see that the call stack was actually coming from a future, not from whatever this method is, run async or whatever. So that's the big problem that you run into in debugging all kinds of code. Now Scala is actually doing some interesting things, or at least looking at doing some interesting things for this. There's some work going on the debugger by some of the type A people who are the main commercial organization kind of pushing Scala, to look at basically structuring the debugger to make sense of these multiple threads of execution and calls that are kind of coming out of sequence. So hopefully they will be doing some things with that will make debugging easier and make it more sensible when we look at breakpoints in these types of code. But for right now, we're stuck with the standard problems of debugging asynchronous code. Oh, and one other thing, you can disable the asynchronous execution. So effectively, for debugging purposes, you can turn off the asynchronicity, there we go. And you can then breakpoint through your code and step through it and everything just as you would linear code. Of course, that doesn't mean that all the problems you're going to encounter can be solved that way. A lot of times you're going to have problems in this concurrent code that won't be repeatable if you execute everything in sequence. But it's at least a useful debugging tool for simpler problems. Now, all these are examples of managed concurrency, what I would call managed concurrency, meaning that you program it step by step what you want to do. Some cases are easier than others to do it, but it's all a matter of you have to specify exactly what execution flow you want to have in order to get things done. That's great for simple situations, but for complex scenarios you run into problems. Blocking approaches, you have to worry about deadlocks, thread starvation, all this sort of thing. All the issues that have been plaguing us with threads all along. Even though some of those issues have gotten simpler over the years, there's still a lot of complexity there. Non-blocking approaches also have their own issues. One is that callback hell that I mentioned, where you have code that's being called from someplace else, triggered by an event that's completely separate. So your call stack doesn't show you anything useful. You don't see the context that you created this event from. You see the actual event execution code that's calling back to you. Code gets cumbersome with many different events involved. So far we looked at very simple structures or parallel programming and that sort of thing, and that's all simple to handle. Building large chains of futures can add overhead. I mentioned how some of these approaches that I talked about are actually constructing new futures and all. When I was writing one of the first articles in my series, I tried with the new Java 8 code doing some computations where I basically chained together composable futures one after the other. And I ended up getting a failure where in some cases it would just go away. It would never come back to me, it would just hang. I talked to the people behind that, luckily, and the people on the concurrency list, and it was eventually tracked down to an issue with running out of stack. I had a stack overflow error going on in the depths of the Completable Future code, but it wasn't actually processing it in any useful way, and so it just kind of threw up its hands and gave up. So it wasn't obvious from what I was doing that I was creating a very long stack or very long chain of completable futures. So you have to sometimes worry about how that's actually going on and what can happen. Now I think the code has been fixed so that it actually will throw a Stack Overflow exception if something like that occurs. But there's probably other cases where you can still run out of resources and stuff will just stop working without any clear reason why. So it's useful to at least think about, is it possible to abstract the management of these events out of the actual code? Well, that's what I see as being where the actor model really fits in well. Now, the actor model is something that's been around for a very long time. It was a theoretical model for analysis of concurrent programming situations and everything from back in the 70s. So it has a long theoretical history going on. As the basic idea is that actors are lightweight entities with some kind of state information, or potentially with state information. You can have many instances of a particular actor type, or perhaps only one instance. It doesn't really matter. Each actor represents some form of processing step. And just what that means is pretty much up to you, as I'll say in some of the other slides. All interactions between actors are in terms of messages. So you receive messages, and typically you do something in response to a received message, which is going to be useful. If you want to initiate something external, you send a message to another actor. So actors are sending these messages back and forth all the time, and in theory at least, you get something done by the composition of all of them together. We have a large body of practical experience with actors from a language called Erlang. Anyone ever worked with Erlang? It was used a lot, it's been used a lot, especially in like the telecommunications industry, since I think about the 80s, I might be wrong about that. But it's been used for a lot of switching systems and things like that I know of. So Erlang has been out there for quite a while. It's still a somewhat popular language, at least it's a language in active use, put it that way. Now Akka is a particular implementation of actors. It's an implementation that works with both Java and Scala applications, though it's somewhat easier from the Scala side, as I'll show you. It's designed to support writing correct, concurrent, fault-tolerant, and scalable applications. So actors, fault tolerance, location transparency, all these are features. It supports scaling both up and out, as they say. Up means adding more resources within the system. You have more cores you want to use, that's great, make use of them. Out means doing something over a cluster, for instance, or spreading out across multiple systems. Applications needing high throughput and low latency are ideal. Okay. Akka Actors. Well, actors in Akka abstract out all these details of threading and synchronization. So you never have to worry about threads or synchronization or anything like that with actors at all. Whenever there is something to be done, the system will take care of assigning a thread to run your actor when there is a message in the inbox or whatever that needs to be executed. And that's it. You don't have to worry about setting that up at all. Though you can, if you want to, control it down to like the execution context level and all that sort of thing. Messages are immutable, so no synchronization required. Well, that's technically not quite true. Messages don't have to be immutable, though Akka wants you to have immutable messages. And there is memory barriers involved, but the memory barriers are handled automatically by the message passing. So you don't have to worry about synchronization at the Java level that you would usually have to worry about threading issues. It provides message guarantees only of at most once delivery. Now that sounds a little bit peculiar if you think about it. At most once. That means that it's not even guaranteeing the message is even going to get there. It is guaranteeing that if it does get there, it won't get there more than once, but that's about it. The reason for that is kind of going back to the issues involved with recovery. If you start doing guaranteed delivery systems, especially when you start spreading it out over a network, you run into all kinds of issues with communications and all that. I'm pretty well aware of those. I just implemented some improvements to the reliable messaging code in CXF for one of my clients. And it is a complex issue. You have to worry about timing, you have to preserve things to some kind of secure storage if you want to really guarantee delivery, all that sort of thing. So Akka takes the approach of, well, we can't really do guaranteed delivery in any practical form that's going to work for everybody, especially when we want to be able to distribute across systems. So we'll just say that anytime you send a message, you have to assume that that message could be dropped on the floor. And you have to program in such a way as to handle that. That involves recovery stuff, which I'll talk about in a moment. So message ordering is enforced between each active pair. That's all. And it has high performance message queues called mailboxes. Basically, no blocking in the path that gets messages into the mailbox and out again. Now actors, how you use them is up to you, depending on what you do. I have some examples here. You can have walk-on actors that just do one thing and then die. So they just come off the street, do one thing, and then disappear forever. Well-known actors that perform starring roles, well, for instance, suppose you have something that is a centralized registry or whatever. Then you don't want multiple copies of that registry probably if it is going to be controlling something important. So you want to have a centralized instance. Of course, you need to have a way of recreating that instance if it does go away, but that's a separate issue. And you can have a pool of actors sharing the same role in some cases. So, for instance, when resources are shared between actors, such as database connections, you don't want to have too many database connections open. You have a limit on how many you can have. You don't want to open and close these database connections, repeatedly. So it's more efficient to just have actors that each manage a connection, and you can scale that to your needs. And people that need to use that connection can send the appropriate messages to it. You always try and keep actor execution non-blocking where possible, because the core of the system is all non-blocking. In your actor code, if you do something that is a blocking operation, it's okay. Akka isn't going to punish you for it or whatever, but you're going to be limiting your scalability of your application by doing that. So in general, you try and keep the actor execution non-blocking. Avoids the overhead and avoids unpredictable latency. That means that you can scale much more easily than otherwise. Now, here's an example using Scala to start with. This uses a little funky syntax, so I'll explain that first. Scala lets you define special characters as operators, or pretty much anything as operators, actually, when you come down to it. So, for those who aren't familiar with it, you can see the bang and question mark that I'm going to use in this code are actually operators in Scala terms. And the bang is an alias for the tell method that sends a message to an actor with no response. Question mark is an alias for the ask method that sends a message and gets back a future response. Tell is really what you want to do rather than asking. Asking is there more as a historical thing, I think. It's occasionally something that you want to use, but in general, I think everybody doing Akka these days considers it's kind of bad form to use ask. The reason being that when you do this, you're setting up a kind of conversation with another actor. You're tying yourself to it in a way. It involves a two-way communication rather than just sending a message and all that. So it's a more complicated case in the internal code, and it has some limitations in terms of performance and all that too. So, all that said, here's the first part of the Akka code in Scala. I set a timeout. Now, another thing that you might not be familiar with if you don't know Scala is implicits. A lot of Scala operations, depending on the type of thing you're doing, may take implicit values. What that means is that it needs a parameter, but it's a parameter that you're generally going to just set once and use repeatedly. So rather than specifying it for every single method call, you just make it an implicit, and it gets used by default. So in this case, I've got a timeout value. I'm just saying I'm going to use a timeout of 2 seconds here, without, for everything I'm doing, unless I specify otherwise. I get an actor system. I put a name on it. In this case, actor demo. I create an actor. The system actor of is saying I want to create an instance of this actor if one's unavailable or whatever. And then I send it a start message. Well, a start message in this case is a case class. In Scala terms, these are kind of the equivalent of immutable Java beans or whatever, data objects. So I have start, generate, number, report, and sum. All right, And that's all that this main code does. It just starts up the actor system, and then it goes to sleep for a while, and it shuts down. The actual actors are on this slide. So I have a root actor, and it has this receive method that in Scala terms is a partial function. Partial function means that it's something that tells you how to handle certain types of input, I guess is the best way of putting it. And in this case, all I'm expecting is this start message. So that's the only message that this root actor is going to be processing. When he gets a start message, he's going to execute this code here. It says, create a summer actor, create a generator actor, and tell it to generate values to the summer. Start another generator actor, and tell it to generate, sending the results to the summer. And then get a result from the summer that tells me what the sum of the values is. And finally, just waits for that. Well, you notice I'm doing blocking stuff in an actor. I told you it's not a good thing to do, so this is just an example, though, and I wouldn't do this in production code or real code. The two other actors I'm using are right here. I have a generator actor that when it receives a generate message, it just increments the value and sends it to the to whoever requested the result. And I have the summer actor that whenever it gets a number message, it adds that to the total. And when it gets a report message, it sends back the result. So, yes, Nimrod.
You have to be careful about any kind of state management within these actors. I mean, so total, for example, is scoped to within the summer actor there, and you have both these messages that are operating on it.
Well, actors, as I said before, they do have state, and it's it doesn't make any difference if you have these other guys, the generator instances, are each going to send messages to this guy. So we don't know offhand what order they're going to execute in or anything like that, but we know that they will send messages and they will go to the summer guy. Now, in theory, I should be allowing for those messages to never get there. In practice, I know that in a system like this that's not distributed or anything, I don't have to worry about that. But in this case, I know that the summer may or may not receive messages. If everything works as expected, it will get 2 number messages, one from each of the generators. And I don't know what order those will be in code, but it doesn't matter, it just adds them up anyway.
That was the question.
Yeah.
It doesn't matter.
Yes.
Yeah, and I think the point is that the messages are serialized, so you don't have to worry about synchronization.
Well, it's not actually serialized. It's just passed as an object.
No, I meant
Sorry.
serialized in the sense that the events don't come simultaneously.
Exactly. It's one at a time. In case I wasn't clear on that, the messages are processed one at a time for any given actor. So you never have multiple threads executing an actor. It's always single-threaded inside the actor. The code, if I had multiple instances of summer, then different threads could be executing different instances simultaneously. But each instance is always going to be single-threaded. Put it that way. Yes?
So it's the same generator that's being used in both of these cases, or is it?
No, I'm actually creating 2 of them.
Okay, that's what I thought. So is
Yeah.
last out then effectively a static variable there, the generator? So it's.
Well, in theory, it's a variable. If I wanted to, I could just create.
So in this case,
I could call each of these generators multiple times.
Okay.
I could modify this and send them each, 2 or 3 messages to generate rather than just one. So you can do it different ways. But in theory, it's reusable and everything like that. It's set up to be reusable. It has state information. In this case, the state is this last out value. In the case of summer, the state information is this total value. So each actor in this case has some stateful information that's part of it. All right. So, other questions about this?
Doesn't the actor have to preserve this? Theoretically, what you're trying to do is avoid deadlocks or atomicity violations, right? You have to preserve the state. That's the.
There's no preservation involved. The actors execute with a single thread of execution, as I said. So, you know, behind the scenes, the most any instance of the actor is going to have is one thread executing it. Now, you could actually switch between threads at different times. So there are memory barriers involved there. But the memory barriers are behind the scenes in terms of that message queue, that inbox or whatever you have. So that's where you get the memory barriers. And that's why it's important that you don't share mutable values between different actors. So that's a no-no. You don't want to ever have mutable values shared between actors. For instance, if I were to make that last out a static var instead, that would be a bad thing. Because if I'm using multiple generators and they, you know, I'm counting on that static var to be consistent, it's not always going to be the case because different threads could be executing different generators. Yes? That's
So if the generator will put some sort of a weight on thread that executes the generator, then Summer will get a report request before it will get any numbers.
Yeah, that's always a possibility too.
That's a certainty.
Yeah. Well, yeah, if I put a weight in there or something, that probably would be. It's a possibility though in any case. If I wanted to make this code bulletproof, I would put in you know, a weight there or something, or another message coming back to the root actor that says that you know, the summer could report its sum back to the root actor with every message it gets, something like that. But this was designed to fit on a single slide. So it doesn't handle all the cases. It's just to show kind of the basic principles in operation. Right? So like I said, it's far from bulletproof code. As you said, there is a race condition in a sense where you could, at least in theory, have you know, the summer report back a result of 0. But that's okay too. You know, there's nothing in the system that says I'm always going to get the result I'm expecting. If you actually run it, though, typically you will see the result of 2. Yes, Sam?
So how is this simpler than the futures and promises?
Well, this is a very, very simple case. But the main thing that I think makes this simpler, okay, this is a very simple case. And it's kind of a trivial case, like I said, designed to fit on a single slide. So it really doesn't give you much of an example of the simplicity of actor solutions. I think we'd have to get into more complex scenarios in order to really understand that. I do have some slides coming up that I talk about that a little bit more, I think. Back there?
I think that what makes actors powerful is that it provides a good way to componentize your code. And then you can easily compose them by sending messages back and forth. So if you remember the slide with the futures, he was composing them all within one method. So the composition of the futures was kind of all intertwined. But here, the actors are related in little pieces spread out amongst the actors. So if you look at one actor, you just know you're getting a message from somebody you don't care, and you're sending a message on to somebody else. It's very simple.
Yeah, that's a very good way of putting it. It's a matter of problem decomposition. Actors, if you can structure your problem, you know, decompose it into a bunch of actors, each one of these is doing something simple, but when you combine them together and have them sending messages back and forth, the result may be very complex. And because they're all operating asynchronously and they're only connected by these message exchanges, you don't have to worry about things like waits for something to complete or anything like that. You can have the completion send you a message instead. I had a question coming back to that.
First time look at Scala, so I have a question that does everything has to start from the root actor?
Oh no, that's just a name I hung on.
But in the case, let's say Summer can send a message to generator, let's
Yes.
say sync up. So
It could. It would have to be passed a reference to generator. So the way this actually works is this actor of creates an instance of an actor.
Mhm.
And it's actually using these props as just a way of passing parameters in, essentially. So the actor of returns an instance of the actor, and then I use the tell method to say, send the generate message, but tell it that it's coming from Summer. So in this root actor, I'm actually kind of lying to the generator actor, or not lying, I'm just telling it that it's getting a message and the response is to go to Summer, not to me. All right? So I'm telling it where to direct its output message to.
What I'm thinking is, because it seems this is a trend promising, you can avoid thinking about threading. But there's one major character for knowing threading is you could actually control a different sync point.
You
So
could.
in this case, let's say if I want Summer to sync up with generator at some points, and there are multiple contexts that they are interacting, how do you gauge that a generator will receive a sync up before sending out
With messages.
with messages?
Yeah, so you use messages in that case. So for instance, if I wanted to be sure that the Summer had gotten the messages I expected, I would do something like have Summer send me a result back to the root actor or something like that with each one it got. Yes?
Yeah, it might help to mention that the context actor of is returning an actor ref.
Yes.
And that you can also pass an actor ref as a constructor parameter to, like, so generator could have a constructor that was some other actor that it needed to know.
Yeah, you can link actors together in a variety of ways. As you mentioned, it's all actor references though that you work with. So you have an actor reference that in Akka terms is kind of a handle for your actor. It's not the actual actor object. It's a hook or a wrapper for your actor object that allows flexibility in how that's structured. For instance, it allows you to distribute the actors across different systems and still have that actor reference send the message across to wherever the actor is actually located. So it gives you a layer of indirection in there that you're working with. But you can pass them around and all that. Yes, George?
So I'm just curious, I've done a distributed event bus, and one of the nice things about it is that you didn't know anything about the different actors. Every piece stood alone.
Yeah.
So, because that's one of the things that always bothered me about the Scala actor model is like, well, I've got this mixture of my actual business logic in with all this actor specification stuff.
Okay. I'm not sure what you mean. You can have, you can have standalone actors in Akka as well, and it's not an issue as far as I can see.
Well, I'm just saying this concept that I'm actually telling it where to go as opposed to having the receiver.
Oh, well, you're
side.
talking about a bus situation.
Right.
So, yes, if you want to set up a bus type situation, you can. You can have an actor that's effectively a bus manager, and everything gets directed to the bus manager, and he sends it out to everybody. That works perfectly fine too. So if you want to set up a bus system, it's pretty easy to do that. There might even be, I think there's probably something like a multicast router or something that you can use directly for that purpose. But it would be easy to set one up if not.
I think it could be done easier because in the end there is a factory for all those actors, and as you create them, you can probably introspect them and understand what kind of messages they can process through the partial functions.
True.
And they can be outer-outer.
Yeah, there's a kind of continuing ongoing discussion about whether actors should be typed or not. Actors in Akka terms, in the way that I'm using it here, they're all effectively untyped. An actor is an actor, and you can send any kind of message to any kind of actor. They may or may not know what to do with it. If they don't, then it'll just get dropped as a dead letter system or whatever, basically. So there has been discussion, at least, of a typed actor system, where you actually associate types with actors and say, well, this is, I don't know what you'd call it, this is a database access actor, or whatever. And that means it accepts these particular messages and everything. And I think there's trade-offs both ways. At first I thought, well, it really should be something more typed, but the more I've gotten into the actor system, the more I appreciate the idea of actors as just being components that you send messages to, and you don't have to define or know in advance which ones they're going to receive. If you're sending messages to somebody who isn't receiving it, then your logging will typically tell you that, and you can find out what's going wrong and fix things quickly. I don't want to continue on too much longer in this slide since I have some more slides to go through. Is there any last question We'll come back at the end, though, for anybody who has questions about any of the stuff. Is that okay?
And there's always beer for questions later.
That's true. Well, I was going to say the beer questions for the people who want to know more about New Zealand. I know we have at least one person who only came for that today. But, all right, here's a Java example. The Java code is actually working pretty much the same way, but it's kind of more complex to set up and all that. So I have the static classes instead of the case classes in Scala terms, a little bit more complex. And this is the logic to actually launch the actor system there and all that. Here's the first part of the Java actors. Have root extends untyped actor and all this stuff for messages. Actually, in this case, I've got a start and a stop message. I don't think I had that in the Scala code, so I do have a little bit more complexity here than in the case of the Scala one. I have a generator actor, and I have the actual summer actor. Well, as you can see, it's a little less elegant in Java, I think, because you have to do all these if-else statements. You can't just do the simple case statement that we have in Scala, where it says, def receive equals case generate, do whatever you're going to do. So there's a little bit more boilerplate involved in the Java code, and that's one of the reasons I think it is cleaner to do things in Scala with that. I'll get back to that. Actor supervision, I'm just going to go through these slides quickly. I mentioned about how you have to allow for things to fail in Akka. The idea is that you have a supervision hierarchy in Akka. And this is something I think it gets from Erlang as well. It's a concept that's been thoroughly tested in these very fault-tolerant systems. And the basic idea is that rather than trying to accommodate every possible little exception or whatever that can come along, you handle failures at a higher level. So for instance, I get a request in for, I don't know, for a particular web service result or something. And maybe I send that off to an actor that's going to get started and everything. And meanwhile, my top level actor that's actually receiving the request in the first place, perhaps sets a timer or something. And if it doesn't receive an expected result back within the timer expiration, maybe it tries again. Or if the actor that tasked it to dies, then it restarts and tries again perhaps. Or maybe it just times out and sends a timeout response to the requester. It really depends on how you want to structure your system to handle the cases. But the idea is that you have a hierarchy of actors, and the higher level actors are responsible for recovering when something goes wrong for the lower levels. Systems and dispatchers. Well, the actor system organizes a hierarchy of actors. Dispatchers actually run the actors, and the actor system configuration links actors to these dispatchers. You have kind of default configuration you get by default. You can also configure it and change stuff in a configuration file or in your code, either way. So it's very flexible that way. Routers actually distribute messages to a pool of actors of the same type. Now this is a specialized kind of thing. Not all of the things that you're doing are going to be using pools of actors. But when you do have a pool of actors, you have a wide choice of ways of routing messages to these. Round robin, small mailbox, all that sort of thing. Location transparency. Well, as I mentioned, everything is done through actor references. So the actor references add a layer of indirection between what you talk to and the actual actor at the receiving end of the queue or whatever. Those may be running on the same system or a different system. You can look up actors by names, and sometimes you want to do that. But most of the time, you're working with actor references that are passed into you, and you just know who you're supposed to talk to. There's something called Akka Io. I talked about this last week at the Scala meetup group, and I'll get the slides up from that sometime soon as well. But basically, it's a way of doing non-blocking network operations in Akka with actors. I have a couple slides that just show a simple example of that. Designing actor systems. Well, the important thing that you have to start with is to forget about all the object-oriented stuff. Actors are not objects. They are execution components or whatever. And you don't want to think of them in terms of objects as being like, I don't know, customer or inventory or anything like that. Instead, they're just processing steps. And that's the way that you want to think about it. So you should start by identifying any potential concurrent operations in your application, whatever that application might be. So processing steps are separate activities, separate operations that can be done, all that sort of thing. Different application events or processing stages in a particular event. So for instance, oftentimes you'll have processing where parts of it can be done concurrently. And if that's the case, then those can be separate actors to take advantage of the potential concurrency. Then you start supplementing with special purpose actors. So initialization actor to set up a main actor. This is often convenient, especially in Scala. Java has the whole null reference thing. Scala doesn't allow you to use null. So instead you have the what's called an option, which is either a value or it's not. And that's fine for what we're dealing with. But a lot of times, if you have some initialization data, for instance, for an actor, it's more convenient to use a separate actor to get that initialization data set up and then create the real actor with all the data passed in. So it avoids having to use optional values. Pooled resource actors for limited resources, well, I mentioned that already in the case of like database connections or, I don't know, web service connections or anything like that. Delegation actors for handling interactions. A lot of times, if you have actors that are doing kind of a scripted exchange where you're going to be doing this with this actor and then doing something else with another actor and something third with another one still, it makes sense to split those up into separate sub-actors and make each little step a separate actor. Facade type actors for control. Well, one example of that is, for instance, for controlling capacity handling or something like that. If you're doing a web service, let's say, and you find you're getting overloaded, maybe you want an actor at the front end that monitors response times. And if response times start getting too high, it starts rejecting requests up front rather than waiting for them to time out or anything like that. So you can add actors in the middle of flows typically to do special purpose type things. So a very flexible system that way. And allows you a lot of nice, nice features for large scale systems. Effective actor designs, well, actor tasks need to be significant processing. Now what does that mean? The overhead of an actor call in JVM is going to be considerably more than a method call, within your own code, but it's going to be much less than, for instance, calling out across the JVM, or even than doing a significant amount of computations. So you don't want to take every method call and make it a separate actor, but on the other hand, anytime there's interactions involved and such, it probably makes sense to make that a separate actor. There is much higher overhead when you're passing messages across JVM, and I have another slide about that in a moment. Low creation and termination overhead for actors. It's very convenient to use one-off actors, and it's not expensive to do that. In Scala, I think the memory size of an actor is about 400 bytes. So it's not a huge object. It's not as simple as like a single string would be. But on the other hand, it's something that doesn't cost you a lot to create and discard as needed. Retrofitting Java applications. Well, I had hoped to have an example of this I could show you, but that's still in the works. I'm going to be using it for one of the future articles in my series, so I will get around to it at some point, and I'll update you guys when I do. But from what I've seen and what I've done so far, it seems to me that it's a very, very good tool for retrofitting concurrency to Java applications. Existing Java applications may not be designed for concurrency in a lot of cases. If you look at the application data flow in terms of actors, you can break down that structure and come up with a way of structuring the application into actors using the existing code. So basically splitting up the existing code into actor-like components. And to my mind, the cleanest way of doing things in Akka with the existing Java application is to use Scala at the top level. So you can take advantage of that nice control flow stuff that I showed you and everything like that without getting wholly into Scala, but just committing to using it at that top level where it's convenient. So if you've been thinking about getting into some Scala code, I think that's kind of an ideal way of doing it. Akka gives you some really great features for structuring concurrent applications, and Scala at the top level allows you to work really well with the Akka system without a lot of boilerplate and all that sort of thing. The WSDL analysis application that I have started on but haven't gotten completely working yet was originally a Java single-thread application. It would go out and read a WSDL that I pointed at and parse it, make sense of the data in it, go off and reference, find other WSDLs that are referenced by the original one and recursively do that. And then once it had all the WSDLs in the set together, it would do a more thorough analysis across documents to make sure it all is consistent. So I'm setting that up as a Scala application, a Scala Akka Java application, and it's all working out pretty cleanly. The most trouble I've had, or the only part I've still got to finish up, is actually decoupling the part of the Java code where it expects to be executing a single thread of execution when it goes off to get a new WSDL. So that's the one part that I still have to decouple. And it's not a huge problem, it's just I've been a little bit busy and haven't had a chance to complete that. So I think that this is a really clean way of doing things if you're interested in going to knock
Could I trivia question there, but
Sure.
Decoupling the existing sort of worker business code, even if you were not retrofitting, do you tend to find yourself just putting that business logic right in with the actor, or trying to decouple that more?
Depends. If the business logic is simple, then you can put it right in the actor. If it's more complex, then there's nothing wrong with putting it externally. And Scala, of course, is completely interoperable with Java. Well, there's some very obscure cases where you get into a couple of issues. But in general, it's very easy to call Java code from Scala, and even to call Scala code from Java. Did I just say the same thing twice? Either way, it works both ways. It's very simple to do that and very clean. So as far as breaking it up, it really depends on your preferences, just like with anything else. Maybe you even want to just have the message handling code in one place and just call a separate method for each, for the actual business logic of each one. It's just your preferences and how you want to structure something. Fine. I mentioned here as well some potential issues. Often the Java code is going to be passing around mutable data structures and everything. That's certainly the case in my WSDL application. In theory, you're not supposed to pass mutable data as messages between actors. In practice, it's not really a problem. The thing that you really need to avoid is sharing mutable state across actors. So when I say that it's okay to pass mutable data, what I mean is it's okay to take a mutable object and pass it on to another actor without holding a reference to that yourself. So you wash your hands of it and turn it over completely to somebody else. That's not a problem, because the coordination, the memory barriers and everything will take care of making sure that the threads are correct in that case. But if you try and share the same mutable data between multiple actors, then you have all the threading issues, and you're going to run into all the problems of sharing data between threads without synchronization. Okay. Distributed Akka systems, well, as I mentioned several times, it supports it supports distributed systems. This is still somewhat a work in progress, but it is at a working stage. It's just that there are refinements that still need to be added and everything. And it's probably not being used at a really large number of sites currently. It's still being rolled out, I guess is what it comes out to. Anybody here from the white pages? No? Okay. Well, white pages are using Akka a lot in their stuff, and they're working directly with type safe people. They've got the support agreements with them. I think from what they said, they're looking at starting some of the distributed stuff, but aren't actually using it yet. But the Akka system is all set up to allow you to work with these distributed systems, and you can set up these clusters to be self-organizing so that nodes can come and go. You can hook in the management of the cluster so that your actors can be notified when something comes in, all that sort of thing. And then some references. Okay, so let's see, how am I doing in time here? We're just past 8:30, so pretty good. If we take like 10 or 15 minutes on questions, I know we had a lot of stuff before, so let's get back to it.
So the distributed systems, that is literally Akka clusters, right? Or
Yes.
is that- And so if we want to have a mailbox that is exposed to more than one JVM, that's what we're going to do right there.
Yeah, that's true. You would have a distributed system. It could be, you know, you could even run it on a single system or whatever, but it would still be across JVMs. So, yes. Yes?
So in a typical system, what does the latency look like? Like how many, if I have a cascade of this event leads to another, how many events happen in?
You mean how many
Hundreds
events
of
or how many messages?
Yeah,
are time?
how many cascading messages can I get across in, a certain number of milliseconds?
Okay.
Where A leads to B
That's
leads
a
to
good
C?
question. I haven't actually timed that. It's something I should probably do for some of the developer work stuff, because I like to throw in timing figures on that. My feeling about it would be that, you know, the overhead is going to be sub-microsecond, certainly, for getting a message from one actor to another. I think it's probably on the order of, you know, a few hundred cycles, but I don't know for sure.
Okay, so there's no guarantee that you're necessarily going to have a context switch from one message to the next.
Typically, you won't have a context switch from one message to the next. That's one of the nice things about it. The way that the system is set up is it will try and run the same thread on the same actor whenever possible. So as long as an actor has stuff in its mailbox, the thread will probably stay with that actor and continue processing stuff for that actor. If there's a pool of actors, then the threads that are executing that pool will stay with that pool as long as possible, as much as possible. So it avoids context switching whenever possible. And it even avoids synchronization. You have some non-blocking barriers there. Some non-blocking barriers with the actual message queues and all that. But it's not synchronizations, it's instead like volatile values.
They have a benchmark of 50 million messages per second on a single machine.
Okay, so there you go. So yes, well sub-microsecond levels, and down into the tens or most 100 clock cycles roughly. Yes.
So in this simple example you showed, you had two messages going in, right? And really the one object should wait for those two messages. Is there a way to synchronize that from the controlling actor, or does this has always to be the receiving actor that has to control how many messages it's going to receive?
Oh, how many messages are going to receive? Well, there is no coordination in that sense. You have to coordinate with other messages. So if we go back to the slide that had the actor code on, I probably shouldn't go too long here. Anyone who does want to leave, go ahead and feel free. Some of you have already, so it's not a big deal. But let's go back to the slide here and take a quick look. So you're saying if we wanted to, for instance, receive two messages only or something like that, and then record?
Right, since it's the controlling actor that is going to determine the number of...
Well, we can put a parameter on the report, for instance, that says, report to me when you've received n messages. I could add a counter here that says how many messages I've received.
Right, so...
No.
That's what
not
means
the way.
that you're
That's
receiving actor.
It's better to have a counter on a summer that will send a result message when it receives the predefined number of answers.
Oh, sure. Yeah, that's another way of doing it. But I'm saying if you just wanted to have reports and control, you could also have the report say how many, at what point it should send the report. And Summer could then maintain a queue of those and say, okay, I need to send this guy a notification when I've gotten so many, values or whatever. So you can do it either way. You can have Summer configured initially so that every two messages it sends off some message to somebody, or you can have the message that comes to Summer that says, tell me when you've gotten this many messages and what the sum is. So either way, it's flexible. Yes.
I think the more subtle problem is that if you have an asynchronous system, you have a bunch of generators running full out, slamming messages into the summer, that they can pile up in the summer's mailbox. And the actors, the user code here doesn't really have a lot of control over the queuing system in the actors.
Yes, this is a much more, much deeper issue. You obviously have been working in this area, so you have some knowledge of this. There are systems being set up in Akka that use what's called back pressure in one form or another. And basically the idea is that you do have to have, in some cases at least, control over the message generation process. And if you have somebody that's generating too many messages, you're eventually going to run out of memory unless you have some way of turning them off. So there are various techniques of doing that. One way is to basically give allocations, I suppose, where somebody gets a permissions token that says, okay, you can send me a message, or you can send me 10 messages, or 100 messages, or whatever, and then they are able to send that many messages, and then they have to wait for another permission token. So that's one approach. But basically the idea is that you have to start having two-way flows of messages to somehow let the sender know when they're overloading you or something. Well, the other alternative is that Akka is not guaranteed message delivery. So if the queues get full, you just drop messages. That's not a problem.
Well, yeah, and that's actually one of the things they say in the Akka documentation is though when you're on the same JVM, it's best effort, which is it's only going to fail if you basically run out of memory.
Exactly. Yeah.
So you're, so that's what's going to
At least
cause
that's
it
the only
to
known
finally
way.
to fail. But if you haven't run out of memory, so but one of the interesting bits is I guess this question about where does how can it be smart enough to not get any particular queue so full that it can't drain the rest?
Yeah. Well, that's actually that's not an issue. I mean, you can drop messages from any queue and it's going to be okay.
Well, you don't want it to, right? I mean, this is the
Well,
thing.
yeah,
This is the question is about what controls are there short of re-architecting your whole program around things like control flow to inform or bias the scheduler so that it's not overloading queues.
Yeah, and a lot depends on your situation too. In this case, we know that these guys are not going to take much time no matter what. Now, if on the other hand, this summer guy was going off and calling a web service for the results of what he was doing, an operation that's going to take a long time potentially, and you had these generators just spitting out messages left and right, you need to have some kind of control there, or you're going to start dropping the messages from the generators because there's just not going to be a queue for it. Now, one thing I was going to point out too, the idea of this failure as part of the system design is something that people find a little bit disconcerting at first. We try so hard in our applications to avoid things failing after all. And it seems like a very bad thing. But it kind of goes back to the whole idea of checked exceptions and unchecked exceptions and all that. Checked exceptions are telling you these are things you need to worry about in the code. And it can get out of hand. A lot of people detest checked exceptions completely because it forces them to deal with stuff just by passing off a lot of times to other things. If you look at the whole internet system and the basis of that in TCP, TCP is a protocol that relies on messages being dropped. What happens is that your bandwidth, that your throttling of the sender in TCP is continually increasing. So the sender, TCP is always telling the sender it can send more data than it sent before until something gets dropped. When TCP realizes that a message has been dropped, a packet has been dropped, then it throttles back and stops telling the sender that he's got all this bandwidth and everything and says, well, don't send quite so fast as you were before. But then it starts creeping up again until the next one gets dropped. So it's interesting that TCP relies on failures because that's how you handle a system where stuff gets queued and stuff gets lost potentially and all that. If losses are going to be a part of your system anyway, you may as well make use of them as part of the feedback or whatever. So I see the whole failure architecture thing as being kind of along the same lines.
So in that case, how do you who handles the errors? If one of those generated messages doesn't arrive at the summer.
Okay.
That's
well,
left as an exercise for the reader.
Right, but who would handle that? Is that the control?
Okay, if you want to make sure that the messages did arrive, well, you'd have to build something into your application that actually guaranteed that. And you'd have to have a higher level control basically that says, okay, I'm an actor that's going to make sure that the proper number of messages get generated. And that actor would actually count the messages, and each time it had a generate message, probably it would get the generate message, and it would then send it on to Summer so that it could count it. And it would get an acknowledgement from Summer to say that actually got it through. So that's one way of setting it up anyway. So basically the solution is always to create another layer of actors.
So does anyone know if are there any example applications out
Like the
there?
direction.
Example applications that show all the, there's tons of example applications to just have like the very basics and then basically say, okay, then, oh, you would probably in a production app, of course, you would try to recover from the error and you would try to do this and that.
Yeah.
So are there examples you can
There
find
was
out
a good
there?
one I was looking at, I listed
Actually,
in the slide references here, I think. You can look it up in the meantime. I'll try and post these as soon as I said. Come on, let's get to the end. Here we go. Scaling out with Akka Actors. I thought this was a very good description of structuring an actor system for distributed architecture and all that. It's a presentation from, what was it from? One of the Akka conferences, I believe. But he seems to go into a fair amount of detail there, and I think he actually has some code as well. There's another one I was going to give you by, was it Kuhn? I forgot now. One of the main people in the Akka community. Oops, I'm getting confused by having multiple things open here. Let's see. Do I have it there somewhere? It might be the effective actor one. Effective actors. Well, Jamie Allen, he's one of the main consultants for TypeState. So he gives some good info on actor patterns and ways of structuring stuff with Akka and all that. There are tons of Akka examples out there, of course, though most of them are pretty simple. I'll try and get my Whistle code example out there at some point. It will mostly be interested in those, showing how you can structure Java code, make use of existing Java code, and putting together an actor system, I think. Nimmer.
You know much about transactional systems and how they interplay with actors and stuff?
Interesting question. Well, Akka actually does have software transactional memory as well.
Okay.
So it does have that implemented. I haven't worked at it. I looked at it a bit, but I don't remember the details enough to tell you. But yeah, if you look under on the Akka site, you'll find. Oh boy, it's hard to do this from an angle here.
Yeah.
But if I go to my friend Google and look for STM. Yeah, so you can find it pretty easily how the STM stuff is set up in Akka.
Yeah, but transaction-wise, like a database transactions, you have to redo everything because there is no thread locals available anymore.
State's kind of
Because
hard.
as you try to coordinate among multiple actors, they execute on different threads.
Distributed transactions. That's the thing.
You do more of the Visa model where you reserve and where like you reserve money for a purchase and then you either claim the money later or you return it to the person.
Distributed.
Is it more that kind of structure?
Whatever you have to do, you will need to change your approach. Today, you just, let's say, start the transaction when you get the request and then stop when you finish handling the request. It doesn't work with actor systems.
But if you're fashionable enough to be using Scala Actors, you're anyways going to be using a NoSQL database that doesn't support transactions. So
Just say no to transactions.
Well, you do a transactional system like that in Akka, you just use the database to actually maintain the state that you're modifying. So I don't see how it's really different from a Java, any Java application.
Well, you have to pass your transaction reference on messages.
Well, I would think that you'd actually have an actor that owned the transaction or something, and
Well, then you pass the reference to that actor.
yeah, it's true.
So it doesn't matter. Either way, you have to do it explicitly versus you know,
It's not
usual
limited.
Java way
Yeah,
when you have that
restructure-
implicit.
Restructure your actors so that you had one actor that was coordinating, and, you know, he was the transaction owner, and all the other actors reported to him, basically. So when there's a failure, you just restart the whole transactional
You
action.
use the supervisor model? and
Yeah, exactly.
that way?
Yeah, it makes perfect sense for that setup.
Supervisor would be the transaction, and he would start off
That's
all
fine,
various
but-
actors, and
but
one
you
of them that fails, he's
But
got to figure
But you
out.
still have to pass that particular database connection to those actors.
All right, sounds like it's
Sounds like it's time
All
for
right,
beer.
yeah,
Time
okay.
for the beer act
We're
now.
getting to the nitpicking stage, so thank you all for.
Thank you, Dennis.